One of the greatest problems for aeronautical engineers is how to keep the parts of a failed jet engine fan assembly from threatening the safety of the plane's passengers or its airframe. To prevent this, a metal or metal alloy case is built around the fan to contain a loose blade or other debris until the pilot can safely shut down the engine and land the plane. During the few seconds while the engine is shutting down, the fan case is subjected to loads far in excess of those experienced during normal flight. To keep the containment case from cracking or failing completely after a loose fan blade has impacted it, this critical component is usually the most over-engineered and heaviest part of the jet. Beginning in the mid-1990s, an innovative partnership made up of members from academia, NASA, and the aviation industry began examining carbon fiber reinforced composite, or CFRC materials, to see if they could provide a viable alternative to metals. This research proved very successful. When used to build jet engine fan containment cases, composite materials were not only better than metal at maintaining the structural integrity of the fan cases, but they could be produced for roughly the same cost. Because composite materials weigh significantly less than metal, they also offer increased fuel efficiency. During the course of their investigation, members of the partnership also developed new production methods for composite fan cases and contributed to the building of an industry-wide finite element analysis tool that analyzes the effect of a fan blade impact engine failure on various aircraft systems. This analysis tool was supported and validated by extensive ballistics testing. After demonstrating the viability of composite material fan containment cases, the partners worked to commercialize these innovative new technologies for use in jet engines for aircraft ranging from small general aviation planes to large commercial airliners. This DVD tells their story.
Good morning, everybody. I'm Chris Scalise, and it's my pleasure to invite you all, invite you all to this segment of the Aeronautics Research Missions Director Technical Seminar. As you saw, the topic today is the evolution of jet engine blade containment systems, and it's further my pleasure to introduce the speaker, Dale Hopkins. Dale has been employed at the NASA Glenn Research Center for over 25 years. During that time, he's held several positions as a research engineer, deputy and acting branch head, and for the past 10 years he has held the position of technical leader in the Structures and Dynamics branch. Currently, under the new NASA ARMD, and for those of you who don't know the acronym, Aeronautics Research Mission Directorate Program Project Structure, Dale is also the Associate Principal Investigator for the Supersonics Project and a Challenge Problem Owner for the Aircraft Aging and Durability Project, where he's guiding teams involved in new R&D for a variety of materials and structures to enable lighter, more durable engines for future aircraft. Mr. Hopkins has received numerous awards from NASA for individual and team achievements, including the Turning Goals into Reality Award in Aeronautics in 2004, the Exceptional Service Medal in 2007. Dale received his bachelor's and master's degrees in civil engineering from the University of Akron, nearby there in Cleveland. He studied advanced studies in mechanical and aerospace engineering at Case Western Reserve University, as well as attending numerous short courses. I'm also pleased to see that he's active in the AIAA and SAMPE. So with that, Dale.
Thank you, Chris, for that introduction. Let me start by saying good morning to my colleagues here at NASA headquarters, and also to my colleagues at the various NASA field centers who may be watching today. I'm pleased to be in Washington this morning. It's a privilege for me to have the opportunity to present the Aeronautics Research Mission Directorate Technical Seminar for September. I want to thank Dr. Porter for the opportunity and the other folks in the ARMD, in particular Herb Schlickenmeyer and J.D. Harrington, who have coached me and helped me prepare for this over the past days and weeks. and also to the NASA TV crew who helped me make some adjustments in the presentation first thing this morning. So if you've watched these seminars in the past, you may have noticed that mine started a little bit differently with the video clip. So let me make a remark about the structure of the presentation. I've actually structured this presentation around several video modules. And I've been able to do this because we recently made a documentary of our efforts over the past 10 plus years. So I've taken select video modules out of the documentary and I'm using them in the presentation. So as the main title implies, we're talking about the evolution of jet engine blade containment systems in general. More specifically, as the subtitle implies, the presentation addresses our efforts over the past decade or so to make advanced composite materials and composite structural configurations safely applied in this application. So the presentation is going to touch on key aspects of our endeavors, the manufacturing process advances, the testing methodology advances, as well as some simulation and design technology advances, all of which has sort of enabled this application to come to fruition. So, next slide, please. We're going to play another module now. It just gives you some additional general background information in what a jet engine blade containment system is and why it's a particularly challenging problem for engine designers. So you can roll this module.
As businesses grow across international boundaries, reliable air transportation is becoming more and more important in keeping our global economy surging forward. While flying is already one of the safest and fastest ways to travel, NASA, the National Aeronautics and Space Administration, is always looking for ways to improve aircraft safety and performance. The Aeronautics Research Mission Directorate of NASA is charged with researching and demonstrating advanced technologies to make aircraft and aircraft systems safer, more efficient, and better for the environment. Researchers at NASA's John Glenn Research Center in Cleveland, Ohio, have been working with aviation industry innovators to examine how using advanced composite materials to build aircraft components could help build better jet engines. The fan case on a jet engine houses a series of fan blades that suck in enormous amounts of air and compress it again and again in order to provide the thrust that propels an aircraft forward. Conventional fan cases are built of thick, strong metal or metal alloy in order to withstand a particular type of engine failure called a blade out. This rare but potentially dangerous event occurs when a bird, hail, or other foreign object is drawn into the engine and dislodges a fan blade. Because broken fan blades and other engine components could pierce the fuselage, hydraulics, or other parts of the aircraft, FAA rules require the fan case to contain the debris until the pilot can make an emergency landing. To meet the stringent FAA regulations for jet engine safety, aircraft manufacturers must conduct blade containment and rotor unbalance tests while operating the jet engine at the maximum permissible RPM. This absolute need for safety means that to contain the debris when a fan blade fails, the fan case is frequently an over-engineered engine part and is usually the single heaviest component of the jet engine. Jet engine manufacturers currently use one of two common fan blade containment systems. The softwall fan case allows a broken fan blade to impact an inner shell, pass through it, then enter into a capture zone in between the fan case's inner and outer shells. Many layers of ballistic fabric wrapped around the outer shell ultimately stop the fan blade. The hardwall fan case is designed to reflect the blade back into the engine. This concept allows for better engine aerodynamics, but the broken blade may pass through the engine, causing secondary damage. A successful design for a hardwall fan case depends on the case being able to absorb the energy from the blade impact with a minimum amount of damage or fracturing. In both the softwall and the hardwall fan case concepts, composite materials were identified as weight-saving materials. But could they absorb blade impact energy as well as metals do? And could they do it without fracturing? This is what the Glenn Center's researchers and their academic and small business partners determined to find out.
Next slide, please. The next couple of slides, I'm just going to reinforce some of the key points that were presented in that video module. Basically, what is a jet engine blade containment system and the two different design approaches that have evolved over the years. This slide shows sort of an artist's simple rendition of a typical high bypass turbofan type jet engine, which is the predominant type of power plant that you see in commercial airliners today. In preparing for the presentation, I went back and reviewed a little bit of the history of commercial jet transportation, at least, and we're actually approaching the 50th anniversary of the dawn of the jet age in commercial aviation. The first jet-powered airline went into service in 1958. It was a Boeing 707, powered by 4 turbojet type jet engines at the time, which turbojets basically are a much simpler jet engine that have no fan. They simply have a compressor, a combustor, and a turbine. But since 1958, jet engines have evolved quite dramatically. We have evolved to this power plant now called a turbofan, which has incorporated a fan in the front of the engine, and the fan has grown larger and larger and larger over the years. So the engines that are flying today are of the type shown here. So what is the blade containment system? If you look at the picture, it's essentially the large structure, the silver-colored and orange-colored structure that appears on the front of the engine. It's the structure, the case structure that surrounds the fan rotor. During a nominal flight mission, the fan case has 2 requirements. It basically confines the flow path through the fan, so it's lightly loaded by the pressure inside the fan. The other requirement of the fan case is that it holds the inlet nacelle structure cantilevered off the front of the fan case, and it holds some of the other surrounding nacelle structure that encloses the engine to provide a nice, clean aerodynamic flow. So those are the 2 nominal design requirements for the case or the blade containment system. The more important design requirement, though, is to meet what's called the blade-out containment requirement. Jet engines can, on rare occasion, experience what's called a blade-out failure event. It's the event where a fan blade were to break off. Thankfully, it's a very rare event. It's hard to find good statistics on the number of incidents in the course of a year that this might occur, but from what I've been able to determine it, you can count it probably in the tens of incidents, or maybe small hundreds of incidents a year that a rotating component, not necessarily the fan blade, but a rotating component might fail in an engine. So when you compare that to the roughly nearly 30,000 flights that are flown on a daily basis on average, it is a very rare event, thankfully. But the potential consequences of the event are such that the certification authorities require that the engine have this blade containment system in place. Now, over the years, as turbofans have evolved, as the fan module has grown larger and larger, 2 different design approaches have evolved to address the blade containment requirement. The original design approach, which in the industry is referred to as the hardwall approach, basically just takes the fan case, preliminarily designs it for its nominal mission requirements, and then just beefs up the structure, makes the structure thicker, adds reinforcing elements to the structure. And in this design approach, when the fan blade comes off, the fragments of the blade essentially reflect off the inner surface of the fan case and then go downstream through the rest of the engine. The more modern design approach, which is called the softwall approach, actually emerged in the early 80s. And this design approach was enabled by some NASA-funded research programs, as a matter of fact. There was a program known by the acronym of QUICSEE, which started in the late 1960s and ran for several years. And it was under that program that General Electric conceived of the idea to put ballistic fabrics into the blade containment system. So the newer engines today, some of the newer engines today incorporate the softwall design. So you have a metal structure that is then overwrapped by ballistic fabrics. The metal structure is there for the nominal duty cycle load requirements. The ballistic fabric is there to contain the blade fragments. Now, the benefit of the softwall design approach is that the overall system weight is lower. It reduces the weight. That's the primary driver for the approach. Also, in this approach, the system is designed so that the blade fragments actually penetrate through the inner wall of the hard structure, and the fragments get captured in this fabric outside of the flow path, so you don't have these fragments going downstream, potentially causing other problems in the engine. Now, composites have been, the appeal of potentially putting composite materials and structures in this application has been around for decades. Obviously, for their better strength to weight and stiffness to weight performance. From what we've been able to gather from the engine companies, and they're very tight-lipped about this particular component. We know of companies who were interested in putting composites into this application as long ago as 25 years. And those early attempts failed rather miserably, mainly because of the state-of-the-art of composite technology at the time, which was manufacture composites in simple intermediate forms, pre-preg sheet or pre-impregnated tow, tape-type intermediate forms, and then build up the structure by laminating these intermediate forms. Those types of composites had very poor impact resistance. So that was the technical aspect that prevented composites from being successfully implemented in the past. There were also other manufacturing and economic considerations because the cost of manufacturing composites back then was much higher and the quality of the end product was lower. So with advances in manufacturing that have occurred particularly over the last decade with the specific materials and concepts that we've developed, we have made the application feasible both technically but also economically and from a manufacturing perspective. Next slide, please.
In this test, a small explosive charge is used to release a fan blade from the disc. The engine has to contain the fan blade safely and also has to contend successfully with the resulting out-of-balance forces. This is a technology in which Rolls-Royce has a clear lead over any other manufacturer. Nevertheless, the fan blade containment test is regarded as an essential demonstration of safety and integrity.
4, 3, 2, 1, quietly.
A released fan blade contains enough energy to throw a medium-sized car some 100 feet into the air. In a full engine test, this energy is absorbed as vibration through the engine carcass, truly one of the most impressive sights in aero engine testing. Without any apologies, we'll show that again. This is indeed one of those occasions when only seeing is believing.
That's footage from an actual engine certification blade-out test, and it's the only footage that I've been able to find that's in the public domain. Obviously, it's footage from a Rolls-Royce test, and I found the video clip on a University of Cambridge website, so I've incorporated it into the presentation. I actually put the URL link at the bottom, so if you want to go out and download it for yourself, you can do that. The U.S. companies have been much more protective about making this type of information available. So, but at the same time, rather than just show complete bias to the U.S. manufacturers, I thought it was nice that we could incorporate this bit of material from Rolls-Royce, since our partners in the UK are interested in the technology we're developing as well. On the left, I've actually extracted the section of the Federal Aviation Regulation that deals with blade containment requirements. And if you look at the paragraph A that's highlighted, it's really quite simple. The requirements are that during a blade-out event, the engine has to contain all the damage, which means all the blade fragments have to be confined within the engine. No blade fragments can escape radially and cause a threat to the aircraft. The other requirements are the engine can't catch fire, obviously, and the engine cannot fail its mounts to the wing. After the initial blade comes off, the trailing blades in the rotor collide with the initial blade fragments. And then instantaneously the rotor becomes hugely unbalanced. And you have this unbalanced rotor that has to continue to run at full power for 15 seconds. That's part of the requirement. And this unbalanced rotor is propagating enormous forces through the associated structure, through the load path structure, through the fan frame and up into the engine mount structure to the wing. So all that structure has to be able to safely sustain the event. The case must have enough structural integrity after this initial hole or damage is caused to the case that it doesn't fail catastrophically. If the case fails catastrophically, it drops the whole front of the engine off, and you can't have inlets falling out of the sky. So that's the key aspect of the requirement, and you can, as you can tell from the video here, it's a violent event. There are a lot of complex physics underneath what's happening during the event. You have the initial blade coming off and impacting the case, causing initial damage. You have the trailing blades colliding with fragments. You have this unbalanced rotor that's whirling, and the whole engine is just shaking, vibrating pretty violently. The premise is what typically instigates this event is the ingestion of some foreign object debris, whether it be hard debris off the runway when the engine's taking off, or perhaps bird ingestion during the climb phase of a mission when the engine's running at peak power, or it could even be during the climb phase, or I suppose in the cruise phase if ice were to be ingested into the engine. It could be either hailstones in the atmosphere or ice that accumulates on the inlet and sheds off and goes into the engine. Now, part of the certification requirements for the engine are also to demonstrate the ability to ingest this type of foreign object debris safely. But these tests are performed once. When the engine passes, it gets its certification. Its airworthiness certificate goes into service. And so there really is no certificated requirement to demonstrate that the engine can sustain these types of events over a long service history. If the engine, experiences foreign object debris impacts over its lifetime, sort of the accumulated effect of that could be to cause a fan blade out event 10 years, 20 years, 30 years into its service life. So Next slide, please. So the next module is going to talk a little bit more specifically about two particular composite concepts that we've developed and the associated advances in manufacturing that have enabled these concepts to come to reality. So you can roll this module, please.
Central to the successful move forward from conventional metal jet engine fan containment cases to new commercial all-composite fan cases are the carbon fiber reinforced polymer composite, or CFRP composite, manufacturing processes being developed by 3 Ohio small business innovators. Because this technology would be applied to fan containment cases being used by a number of different aircraft engine companies, NASA researchers needed an economical, automated method of producing carbon fiber reinforced fan case preforms of varying size and shape. Further, these preforms had to be robust enough to be shipped to various fabricators for conversion into a composite product. The structural reinforcing properties of braiding led to the identification of A&P Technology of Cincinnati, Ohio, as a supplier of preformed fan cases. Braiding can be formed into virtually any shape, even one as complex as a fan case cylinder. A&P's triaxial braided fabric provides a much stronger architecture than either woven or stitched fabric. In addition, the braiding technique can keep preformed CFRP tightly wound throughout the further steps in the composite manufacturing process. Triaxial braided composite preforms are braided with 3 sets of yarn into a series of multi-directional plies, each having identical properties. Testing has shown that braided composites provide increased interlayer strength and damage tolerance far exceeding that of standard layered composites. A stiffening or nesting phenomenon at the ply interfaces limits cracking. A&P's innovative Mega Braider was designed to braid triaxial fabric. This very complex machine can be loaded with up to 800 spools of carbon fiber yarn. It braids the carbon in close proximity to the capstan around which the braiding is being wound. The capstan has the exact profile of the particular fan case being produced, and the fibers being braided can be shortened or lengthened as the circumference of the fan case increases or decreases, and the thickness of the plies can be increased where greater load tolerances are needed. The resulting braided preform is extremely stable. Its shape does not loosen or slip after the preform is moved from the capstan onto a transport cylinder. The hardwall fan case preforms are shipped to the component fabricator, the North Coast companies. North Coast Tool and Mold contributed to the success of the hardwall composite fan case with its innovative resin transfer, or RTM, tooling. The preform is wound over an inner mandrel with the same shape and profile as the containment case, and then placed within an enclosing multi-piece outer tool. The outer tool holds the material taut during injection and cure, and creates a flange of uniform and robust thickness through which attachment holes can be drilled. The flange tensioning is a mechanical process that minimizes variables in the flange layup process. The smooth fabrication and handling will allow cost-efficient out-of-press RTM molding if North Coast Composites prepare to fabricate the fan case in production quantities. The manufacturing process itself also brings about weight reductions. Because the fan case is made in a single 360-degree piece and not bolted together like a metal case, some additional hardware can be eliminated from the system. The airflow through the case's smooth inner surface also allows for some noise enhancements. WebCore Technologies of Miamisburg, Ohio developed a damage-tolerant structural sandwich core material called Ti-Core that is considered well-suited for use in softwall containment systems. Ti-Core is a carbon fiber reinforced closed-cell foam sheet that is wrapped around an inner mandrel in the shape of the fan case. A vacuum infusion process then fills the hollow cell spaces between the fibers with resin. The resin-impregnated sheeting is heated to 175 degrees Celsius, expanding the inner metal mandrel. As the mold cures and cools back down to room temperature, the composite maintains its new shape, while the mandrel shrinks back down, allowing for the easy removal of the fan case component from the tool. Ballistic testing of this prototype showed localized damage where the fan blade penetrated the skin of the case, but damage was limited, and the overall integrity of the case was well maintained. This soft wall system has a 25 to 50% weight reduction when compared to metal fan containment systems, and its retention of mechanical properties during a projectile impact test was twice that of metal.
Next slide, please. So that module introduced the basic two concepts that we've been developing and the innovations in manufacturing processes that have enabled those concepts. There's the fiber braiding concept, and then there's the fiber reinforced foam sandwich concept that have been developed sort of in parallel but on independent paths. So the next few slides just sort of get into a little bit more technical detail about these processes. The two pictures shown here show the braiding machine at a little wider view, so you get a little better sense of the scale of the machinery and the way the process works. You see at the bottom of the picture on the left-hand side, there is this large diameter circular track that carries the spools of individual spools of carbon fiber. And the particular company we've worked with in Cincinnati, A&P Technology, has developed what they call the mega braider, and it's the largest braiding machine known to exist, at least in the United States. It can carry up to 800 individual spools. Those spools actually travel around the circumference of that ring. Half of the spools are traveling in the clockwise direction, half are traveling in the counterclockwise direction, and they're traveling on serpentine paths so that the spools are sort of bobbing in and out of each other, forming the braid. Those interleaved yarns are forming at the braid formation point a little bit above where the spools are, which is a smaller diameter ring where all those fibers come together and they form a very tightly a very tight fabric architecture, as you'll see in a subsequent slide. And then, so we're forming a tubular braid, and it's being rolled up on this capstan winder, and that winder has been made in the exact cross-sectional shape of the fan case that's going to be manufactured. One of the appealing aspects of braid is it's highly conformal. It adapts to the shape that it lays on very nicely without causing wrinkles and other problems like that could lead to manufacturing defects or manufacturing quality issues. So we're conforming this blade, rolling it up on the capstan. That then, in a real production mode, would get shipped to a company that does the molding process, and you saw that in the video module also. And on the next slide, please, you'll see a little bit more detail of the actual fabrication of the structure. So you see on the left, the composite braid has been laid up on the inner tool, the molding tool. In this particular concept, we're using a resin transfer molding process, which is a closed molding process. So you have a two-part tool. You have an inner tool that you put the preform on, and then you enclose that in an outer tool. You hook up the resin lines and the vacuum lines, and basically inject resin at a high temperature and high pressure. This resin transfer molding process is known to create high-quality parts. You get good infusion because of the details of the process. But it does tend to be a more expensive process because of the tooling costs. So the picture on the right-hand side just shows a close-up view of the braid architecture. You can see it's a very tight, in terms of fabrics, it's a very tight fabric architecture. You have very little openness, so to speak, in the fabrics. Next slide, please. The other concept is a different approach. Whereas we're targeting this braided preform concept to make structures that would eventually go into this hardwall type case design, where you have thicker structures that would just consist of multiple layers of braid, where we're fabricating a complete dry preform of the structure and then infusing that with resin. That process is highly automated and streamlined, so that the manufacturing costs are lower than they would be for the more traditional approach to making composites, where you're taking intermediate forms and applying a lot of hand labor to lay those up into a structure. The other concept is geared more toward building a sandwich structure, and this sandwich structure is being geared more towards the softwall design approach, where we're going to let the blade actually pass through the structure and be captured in fabric that's wrapped around it. So we've worked with another small company in the Dayton, Ohio area, Webcore Technologies, who have innovated this manufacturing process to place fiber around and into foam in a very novel way to make composite sandwich structures. And the pictures you see here, the top left picture shows the very beginning part of this process. The process starts with large sheets of foam that are cut into small strips. And these strips of foam are spliced end to end to make just a long continuous, they call it a foam snake. And those foam snakes are put through a filament winding process. Carbon fiber is wound around the individual snake. They call that the composite snake. And that composite snake is then wound up on a spool, basically just for carrying purposes. In the picture in the upper right, you see where we're actually building up the structure now on the tool. So you typically lay dry fabrics on the inner surface of the tool, and then you take the fiber snake off the spool and you continuously helically wind it over top the inner fabric, and you can build up multiple layers if necessary. Then you lay fabrics on the outer surface. Take that entire preform off the molding tool, and it is put through a radial stitching process where you can put carbon yarns as stitches through the thickness of the structure. So you're adding additional features to the preform that once it goes back onto the tool and into a molding process, all that fiber that's wrapped around the foam and those yarns that are stitched through the thickness become basically composite elements. So the winding creates composite webs, and these stitches create composite ligaments that are embedded in the structure. And you can see on the lower right, that is the finished dry preform after it's been stitched and now ready to go into the molding process. So the next slide will show the actual molding process. Now, for this concept, we're using a different molding approach. This is an open molding approach where you have the preform on an inner tool, and then it's vacuum bagged. You hook up vacuum lines and resin lines, and you actually suck the resin into the preform using a vacuum system. But the resin infuses along all the fiber areas, the inner and outer faces, the windings on the foam. It fuses along those fiber paths and also into the yarn ligament stitches. So you get this cured part that's shown in the picture on the right here. Next slide, please. Both the concepts, both the braided concept for a hardwall design and the fiber reinforced foam concept for the softwall design, have proven to be extremely damage tolerant and have high impact resistance, which really is the key feature about these concepts that make them work in this fan case blade containment application. The next module, we'll talk a little bit about the testing methodology that we have evolved over the past decade that has enabled us to, in a much more efficient way, get an understanding of how these concepts perform at different scales, all the way from a material scale up to a sub-element scale where we're testing simple forms like flat plates or simple curved panels, all the way to a full-scale prototype case form in ways we've used ballistic testing and structural testing to demonstrate the performance capabilities of the concepts. So you can roll this module.
Ballistic testing of the composite materials used in these new fan containment cases began with the damage testing of flat panels of the composites and comparing the results against tests of conventional fan case materials, such as aluminum. A gas gun was used to shoot metal blade projectiles simulating fan blades at panels made of aluminum and carbon fiber reinforced composite. The hole sizes in the composite were much smaller. Since the curved shape of the fan case helps reduce stress levels after a blade-out event, this was encouraging to investigators, and the research and development went forward. Impact tests must be conducted under conditions closely mimicking impact dynamics in actual engine fan blade failure. The paths taken by the released fan blade can be complicated. The blade's trajectory, its linear speed and direction, and its rotational motion must all be integrated into the impact scenario during more advanced ballistic testing. In order to achieve the understanding necessary to carry this impact testing program forward, researchers studied various blade-out scenarios using a program called LS-DYNA, a unique analytical code developed by Livermore Software Technology Corporation. Results of this analysis were then used as the basis for designing the impact scenarios for the additional ballistic tests. After initial blade impact testing during NASA's full-size case testing program, the fan case was loaded in a manner similar to that experienced during the post-blade loss scenario. A cyclic orbit fatigue test, representing the number of cycles experienced by the damaged case during engine shutdown, was performed. Damage propagation was then measured and analyzed to understand the success or failure of the containment casing and to predict future performance requirements. Both softwall and hardwall fan cases were tested. In both designs, the engine case had to maintain structural integrity after impact and withstand the rigorous loads imposed by an out-of-balance rotor. Subcomponent level tests of the prototype engine cases by Glenn and aircraft engine companies assessed both the impact response and the case's post-impact structural integrity. Subsequently, full-scale prototype composite containment systems were evaluated and compared in side-by-side tests with existing conventional engine containment systems contributed by General Electric, Honeywell, and Williams International. The NASA Glenn Research Center in Cleveland, Ohio has both the testing facilities and the experienced research staff to perform development tests. This can help save component designers time and development costs by eliminating the need for some of the intermediate testing.
Next slide, please. So the next few slides will just talk a little bit in more detail about the testing approach or the testing methodology that we have evolved to be able to evaluate the performance of these concepts in a very efficient way. We do a lot of ballistic impact testing. We have implemented a ballistic impact lab at Glenn where we have gas guns of various sizes. The picture shown here on the top picture is a picture of our large gas gun. We have barrels ranging in size from 8 inches in diameter up to 16 inches in diameter, so we can shoot realistic blade-type projectiles into specimens. The smaller gun shown at the bottom, which is somewhat unique in that it shoots into a vacuum chamber, enables us to do more sub-element or subscale type testing where we're shooting more simple projectiles into simpler sub-element type specimens, either flat panels or curved panels. Next slide, please. Now, before you panic at the details shown on this slide, it's really here just so that I can sort of give you somewhat of a historical perspective too about our efforts. We actually went into the engine containment R&D business, so to speak, about 15 years ago. NASA had an in-house R&D effort, or dabbled in containment even prior to that. But we really started a concerted effort in the early to mid-90s under the High-Speed Research Program, where we were teamed up with General Electric and Pratt & Whitney to explore new materials and new structural concepts that could make for a lightweight fan case blade containment system on a future supersonic vehicle. Because of the baseline vehicle design or concept at the time, the Mach speed range that the vehicle was going to cruise at, and the engine cycle to enable that, we were pretty much restricted to metallic materials because the fan temperatures were approaching 600-700 degrees Fahrenheit. So we were more or less prohibited from looking at lightweight polymer-based composites under that program. And we didn't get very far anyway because that program was canceled. Obviously, we all remember the fan containment part of the program was the first to get canceled. So at that point, we turned our attention away from supersonic vehicles back to subsonic vehicles, and really made the strategic decision to explore in a very intensive way how we can get polymer-based composites into these systems. So the graph shows sort of how we got started exploring concepts. So for the first few years of our efforts, what we tried to do was explore the widest range of materials and configuration concepts as practical, using a wide range of different materials, everything from metallics to polymers and composites of both, even concepts that incorporated ceramics in a limited way. And the sub-element or subscale testing we did on simple specimens is portrayed in the graph, where we plot on the y-axis impact energy or threshold energy versus the aerial weight of the material or concept. So the best place to be on this graph is in the upper left quadrant, obviously. The lighter aerial weight and the highest energy absorbing capabilities of the particular material or concept. And as you can see, just from and this is only a partial list on the left in the legend, we explored dozens and dozens of different materials and concepts before it became apparent that these two lightweight composite concepts really were showing promise as sort of the best concepts out of the group, both for technical performance reasons, but also for, as I mentioned earlier, for manufacturing and economic reasons as well. Next slide, please. These are just two short videos of typical sub-element type tests here. On the left-hand side, we're seeing a test on a simple aluminum plate. Aluminum is very prominent in fan cases today, aluminum alloys. And the video on the right shows a comparable test of this braided composite concept in a flat plate form. And you can see in particular, the fail characteristics are quite different between the two, and it was this impact resistance that we observed with the composite that really made us excited about the potential of this material. Next slide, please. This just shows another picture of our test configuration. You can see the fixture that holds the specimen, and behind that is a container that holds our high-speed cameras. We use high-speed cameras in a big way to gather data from the test. Next slide, please. In about 5 years ago, we became aware of a fairly new measurement technology called image correlation. Uses digital cameras set up in pairs to look at a specimen during a test, and it basically, you put a speckle pattern on the specimen, and the camera is basically frame by frame watch the movement of those speckles. Using image analysis software, then you can discern the deformation of the specimen during the test, and from the deformations you can compute strains. So this has proven to be an immensely helpful technology, measurement technology for us, because prior to this we were restricted to trying to use strain gauges to measure strains and accelerometers to try to infer forces that that the specimen experiences during a test like this. And strain gauges, especially in the vicinity right at the impact, just don't survive. And they have limited measurement capabilities anyway. So this has really been an immensely helpful way of gathering full field deformation measurements, which then allows us to to compute strain information. So we're getting more accurate measurements, and these data help us validate the models that we've been developing that we'll talk about in a few moments here. Next slide, please. So this just shows a little bit more detail of this optical measurement technique. On the left, you see fringe plots that basically show bands of equal deflection. So you get a sense of the full field measurement capabilities of the system. And then on the right, you see these are actually time histories of the deformation at a specific point. So the technique also allows you to track the time history of the deflection at a specific point versus the full field deformation. Next slide, please. Having identified these two concepts, the braided preform concept and the sandwich concept, and realizing the promise they showed, we thought, okay, we need to step back and really try to understand why these systems are performing so well. So at this point, we started really looking at details that would affect their performance. So the three factors that really are going to affect their performance are obviously the yarn, the carbon yarn that you start with, and the particular choice of resin that you make, and then also the braid architecture. You can achieve a certain range of variety in the braid architectures in terms of the off angle of the bias yarns. So at this point, we did sort of a design of experiments and started exploring the factors and which factors had the most influence on performance. And we learned things that were very subtle, actually, about how these factors influence impact resistance of these materials. You can see the two pictures on the left are using the exact same braid architecture with the exact same carbon fiber. The only difference between these two are the choice of resin. And you can see a dramatic difference in the failure modes in these two specimens. So you see just the selection of resin has a big influence on performance. If you compare the middle picture with the right-hand picture, the difference is the braid architecture. So we've taken the same carbon yarn but put it into two slightly different braid architectures where you have the bias yarns at plus minus 60 degrees versus the bias yarns at plus minus 45 degrees. Same resin in this case. And again, you can see a very dramatic difference in failure characteristics just from what you would think was a subtle change in the braid architecture. Next slide, please. So in addition to putting composites into the hard structure of these systems to replace metal structures today, we're also interested in newer fabrics that could be incorporated into the softwall design approach. So Kevlar is used in systems today. There are new fibers that have been developed since Kevlar. One in particular called Xylon has shown a lot of promise as a fiber for ballistic fabrics. So we have also done an immense amount of fabric testing, dry fabric testing, doing impact tests. And this slide shows comparison of Kevlar performance versus this new Xylon fabric performance. Similar to the chart that was, or the graph that was shown earlier, where we're comparing energy absorbing capabilities of one fabric versus another as a function of numbers of layers. So you can see Xylon is showing performance capabilities up to 3 times that of Kevlar. And then the pictures on the left are just 3 frames from a typical test where we shoot a projectile into dry fabric specimens. So next slide, please. Just similar data, more fabric testing, but where we're looking at the effect of how the projectile is oriented when it impacts the fabrics. Do we have sort of an edge-on impact type of event, or do we have more of a blunt face-on type impact event? And what the data seems to show is that Xylon performs even better for a blunt or for an edge-on impact because it's known to have higher cutting resistance. The fiber is so for a sharp edge-on impact, it performs quite better than Kevlar. For a blunt impact, it still performs better, just not as much better than Kevlar, because the failure mechanisms, obviously, of the fabrics are different depending on those 2 scenarios. So, next slide. So from there, we stepped back even further and thought we need to really look at material characteristics on a smaller scale. We really want to understand how these composites behave at the material level. So we started developing new test techniques that would give us that information. Now, obviously, the key physics to this application are high strain rate response. When the blade impacts the case, right in the immediate zone of that impact, the case materials are being strained at very high rates. These are rates that can get up into the 1,000 or more % per second versus typical static rates, which are 10 to the minus 3 per second. So, and what we learned was that these braided type composites have unique material test requirements. So we had to design new specimen geometries, for example. Some pictures are shown here of, we call it the bow tie specimen design, geometry design, and able to get good quality data on how these materials behave. The picture on the right shows a unique apparatus for doing high rate testing called a Hopkinson bar. It's a very unique apparatus required to impart a high strain rate into a simple material test specimen, higher than what you can achieve with a typical load frame, servo-hydraulic load frame, for example. Next slide, please. So these are just graphs of typical tests. The graph on the left shows just a plain resin, no fiber in it, plain resin, simple specimen, tested at different strain rates. And it's obvious from the curve that the strain rate dependent behavior of the resin is quite dramatic. So this is part of the underlying physics of why these materials behave differently at different strain rates. The graph on the right shows us a similar result for a simple composite. This would be just a unidirectional composite that's tested at different strain rates. So you can see, again, the response, the shape of the stress-strain curve, the values at the failure point in terms of failure strain and failure stress are quite different for a composite loaded at different strain rates. So this is the physics then that becomes important to try to incorporate into new modeling tools. Next slide, please. Then these are just graphic portrayals of what was introduced in the video module, talking about how we use ballistic testing to simulate the damage that occurs during a blade out in a much simpler way. And then we use this post-impact cyclic orbit testing that attempts to simulate the unbalanced forces that the case experiences during an actual blade out event. And we've been able to use these two test testing approaches, which are much simpler to conduct than either a fan rig type test or obviously a full engine test. So it's much more time efficient and cost efficient to do these much simpler tests. But we've been able to sort of fine tune the test approach to very closely match both the deformation and the failure mechanisms that are observed during a real engine blade out test. Next slide. This shows similar pictures. I included this because it shows an actual metallic fan case in the picture on the right. It's mounted in this orbit load rig. I just wanted to make the point that we have brought in engine company partners in this endeavor as early as we could get them interested. They get excited about the potential of these materials, and we get them to the point where they're willing to donate real engine hardware. So we're doing actual side-by-side comparisons, so to speak, where we take current hardware that's in production, test it, and then we test prototypes of these advanced composite concepts, and we can get a apples-to-apples comparison of how much better these composite concepts are. Next slide, please. So I made the point that we have fine-tuned our testing approach where we can use sub-element testing on simple flat panels or ballistic testing of full case prototypes, and we can match the deformation and failure mechanisms across these different scales. So in this way, we're confident that we're representing the physics of the real event in as close a way as possible using these more simplified testing approaches. And that's sort of what this slide was meant to portray. Next, please. Again, just some more details showing how we're matching deformation modes and failure modes on a sub-element scale with deformation and failure modes on a full-scale prototype scale. Next slide. Now we'll talk a little bit about the simulation and design tools that we've been developing in parallel with both the manufacturing advances as well as the testing advances. So you can play this module, please.
NASA Glenn Research Center initiated an effort to reduce risk by teaming with the aircraft and engineering software industries to develop a common structural analysis tool. Previous to this, each manufacturer in the U.S. and overseas was developing and maintaining its own structural analysis capabilities independently. This led to high software development costs and limited the ability to exchange models and simulation results among manufacturers. A team including members from NASA Glenn, GE Aircraft Engines, Pratt & Whitney, Boeing Commercial Aircraft, and MSC Software, as well as international partners, is working together to enhance and validate a general-purpose finite element code called MSC Nastran. These enhancements will enable MSC Nastran to be used for a broader range of engine and aircraft structural analysis. Specifically, this common industry-wide accurate structural analysis code will be used to simulate blade-out events and aircraft vibrations. The enhanced code can simulate engine airframe structures during steady-state and transient operating conditions. For steady-state simulations, the code can predict critical operating speeds, natural modes of vibration, and forced response, such as cabin noise and component fatigue. The simulation code also predicts response during transient operating conditions, such as blade-out events and subsequent engine shutdown and windmilling. The enhanced codes analyzes structural loading from both the impact of a released fan blade onto the fan containment case and the subsequent instantaneous unbalance of the rotating components. The results generated by these system analyses supply critical information to the component design teams for every airplane structure, including the engine, nacelle, strut, wing, and the aircraft fuselage. When compared to the mechanical testing of actual aircraft components and subsystems, a reliable computer model can substantially reduce development costs. Accurate computer simulations of blade-out can both guarantee successful FAA blade-out certification testing and ensure structural integrity during flight. MSC Software will maintain, market, and distribute this version of NASTRAN worldwide. Every major commercial aircraft engine and airframe manufacturer in the world has plans for implementing this code into their design process. This code and its new capabilities extend beyond aircraft structures.
Next slide, please. Just a few more details. This will be shorter than the previous modules, but just a few more details on our modeling efforts. We've taken sort of a similar approach to modeling that we've taken to testing. We want to evolve a modeling approach that takes into account what's happening at the different scales of the problem. You can think of a blade-out event as having really two parts to the problem. You have the localized impact mechanics problem where the blade hits the case. And then you have sort of the more global problem after the blade comes off, where you have this unbalanced rotor vibrating the daylights out of the engine. So it's a problem on a much bigger scale. Well, we're trying to address both problems. For the impact mechanics problem, next slide please, we're actually taking what we call a multi-scale modeling approach. So we start down at the scale of an individual yarn. You can take these carbon fibers are typically multi-filament type yarns. We're using yarns that have up to 12,000 individual little filaments. So we're taking an individual yarn and treating that as a simple composite element unto itself. So once it's infused with resin, it basically becomes like a composite strand or a composite ribbon. And we have developed models that represent the behavior of the composite at that level. From that point, we step up to the next scale where we take a representative volume of the braid architecture, and it's the smallest piece of the braid that's representative of the periodic structure of the braid. So you can see it incorporates axial yarns as well as the bias yarns. That's shown in the picture at the upper right there. So at this point, we're treating the material more in a numerical way than in an analytical way. So we take a typical finite element approach where we can each composite yarn becomes sort of an integration point in a finite element scheme. And we can divide up that unit cell of the braid into subcells, and each subcell incorporates multiple integration points to represent the different orientation of the composite yarns. And in this way, we're developing a constitutive model for the material from the basic level of the individual fiber and the resin and the properties of those two distinct raw materials, all the way up to the basic form in the braided fabric form. And from there, we move up to the next scale, which really is the structural scale, where we have finite elements that have all these details embedded in them. And it gives us a way to predict the performance based on the simple characteristics of the material, the individual properties of the raw materials, and the way they're put together. And we have embedded this methodology into a specialized commercial finite element code called LS-DYNA, which is used widely for impact problems. For example, in the automobile industry, they use it for crashworthiness. So it's probably one of the most widely used finite element softwares for impact type problems. So for the other part of the problem, the bigger problem, the system structural dynamics problem, we are actually using MSC NASTRAN, which is probably the most widely used commercial finite element code. We made the decision to develop these methods and embed them in commercially available softwares intentionally for the purposes of transitioning this new modeling technology to the ultimate end users, who are the engine companies. we were able to get all the major engine manufacturers to agree to a common standard, which we have developed for modeling this problem. So they have all gone away from their own individual approaches to modeling the problem and have adopted this now as a common standard. So pretty much across the engine industry, everybody's using this new common tool set, so to speak, as part of their product design and development process. Next slide, please. These are just pictures of where we are in terms of the state of the art of modeling. This just shows a full prototype with an individual blade on a rotor coming off. Next slide, please. And then this is a simulation of an actual full-scale prototype case with a complete fan rotor, where you have the initial blade coming off, impacting the case, the trailing blades colliding with that, and we're able to predict with really pretty good accuracy the physics of this entire event on this scale. So we've made a lot of progress in terms of the credibility of being able to predict the event. Next slide, please. This just lists some of the specialized features that have been incorporated into MSC Nastran for predicting the big system dynamics problem. I'm not going to read them all, but part of the physics, other than the impact and the unbalanced forces, are you have this rotor that's spinning and it's rubbing. So one of the key things that we have incorporated is the ability to represent that rubbing of the other blades. As the rotor is whirling, it's colliding with the case, and that rubbing causes large torque forces basically on the case. So we have been able to incorporate that rubbing phenomenon into the modeling approach as well. So next slide, please. We're getting down to the end. I have a couple remaining modules, and then we'll close up the presentation. The next module talks a little bit more about the partnerships we've formed with all the different industry and university partners that we work with in developing all of this technology. So you can play this module, please.
The NASA Glenn Research Center is collaborating with several companies in the Great Lakes region under the umbrella of the Small Business Innovation Research Program, or SBIR, to develop fan cases made from composite materials for jet aircraft, which are safer, more efficient, and more environmentally friendly. Aircraft engine companies, Williams International, Honeywell International, and General Electric Aircraft Engines International are helping to commercialize the composite fan case system technology by evaluating it on their own engines. A&P Technology of Cincinnati, Ohio, joined the NASA Glenn Materials and Structures Division to search for lightweight, affordable composite materials for building fan cases in high-bypass jet engines. A&P had just invested in new equipment for the automated braiding of large-diameter carbon fiber sleeves, which could be adapted to produce the triaxial braided preformed composites that were being considered as a solution. A&P's SBIR Phase 1 and 2 research produced several prototype materials that would weigh at least 30% less than the metal fan containment cases in current use. In the commercial phase of SBIR, A&P is partnered with 2 U.S. engine manufacturers. Williams International is responsible for evaluating the technology for product applications, and jet engine builder GE. GE is also using this technology for the fan case on its new GE NX engine, which is scheduled for certification in 2007. Webcore Technologies of Dayton, Ohio became an SBIR partner because of their development of a fiber-reinforced foam composite material called Ticor. The Materials and Structures Division at NASA Glenn identified this reliable, damage-tolerant structural sandwich core material as ideal for soft-wall jet engine fan containment systems. Further research has shown that fan containment systems using Webcore's tie-core weigh 25 to 50% less than those made of metal. At the same time, subscale projectile impact tests have demonstrated a twofold increase in structural integrity. Webcore earned an Ohio Emerging Technology Award in 2002 and has now transitioned to SBIR Phase 3, where its technology is expanding from NASA into other government and non-government applications. The companies of North Coast Tool and Mold, and North Coast Composites were also key SBIR partners. North Coast Tool and Mold of Cleveland, Ohio designed the composite fan case tooling, and North Coast Composites helped develop the resin transfer molding used in completing the manufacture of a prototype hardwall composite fan case after it was preformed by A&P Technologies' triaxial carbon fiber braiding machine. Another partner in the commercialization phase of the SBIR program is Williams International of Walled Lake, Michigan. This company is a world leader in the design, development, and manufacture of small gas turbine engines. Williams is considering using this revolutionary hard-wall composite fan containment system on its new family of jet engines, where it is expected to weigh up to 40% less than metal fan case systems. This reduction will allow improved fuel efficiency while increasing engine safety. By utilizing Glen's unique facilities and by combining their expertise and financial resources, Glen, industry, and academia are able to develop new and innovative products. One result is that these fledgling companies develop the expertise and resources to become suppliers to commercial engine companies. In 2004, the NASA Glen Center's jet engine containment concepts and blade-out simulation team and their industry partners were given the 2004 Turning Goals into Reality Award, NASA's TGIR, in Washington, D.C. Together, all the SBIR partners have developed and built safer, stronger, more efficient, and more environmentally friendly composite fan case systems for jet engines, while at the same time being responsive to President Bush's executive order directing the SBIR and STTR programs to encourage innovation in manufacturing.
Next slide, please. I think what I want to do is sort of wrap this up quickly. There are 3 engine companies now who are serious about incorporating this technology into their products. General Electric is probably the furthest along. They have actually committed to putting a composite fan case into their new GE-NX engine, which is the engine, one of the 2 engines that will power the new Boeing 787. They are in the final stages of their certification process. So this engine should be certified within the next month or 2. And then the engine will be shipped out to Boeing and will be used in certification of the airplane with the engine installed. So Williams International has actually certified a case already for an existing engine product line. And they're developing a derivative engine product that will use this technology. So they're on the path to certifying this technology into their product. Honeywell is another engine company and that's interested in this technology for their products. They're pursuing it for certification purposes as well. Next slide. Next slide. I want to jump to the end and just wrap this up. This is just a list of some of the partners who have been involved. Next slide. Let's skip over this module and we'll just jump to the next slide. So the benefits. Obviously, we're taking an immense amount of weight out of this component, which plays out in terms of individual airplane, but also fleet benefits. Reduced weight means reduced fuel consumption, reduced emissions, enables airplanes to have greater range or more payload. So the system benefits are significant. The other benefit that might not be so obvious is, we believe at least, that we have improved safety by reducing the risk, in the sense that we have enabled these new materials to be safely implemented. These are materials that have greater impact resistance. We've developed design simulation tools that more credibly predict how these materials will perform in this application. So we have reduced the technical risk that would otherwise exist in the design development process for the product. Next slide. So, what are we doing now? We've done all this work over the past 10 plus years. Under the new programs, there is additional research that needs to be done. These composite cases are going into service soon. There has been really little attention given to how they may age or degrade over time. So a focus under the Aircraft Aging and Durability Project is to really seriously investigate the effects of cyclic environmental exposures and cyclic loading over long service times, and how that may degrade the performance of these composites in this application. Under supersonics, we would like to basically take this technology and move it to a high temperature capability. So we're looking at higher temperature resins, and can these particular manufacturing processes be adapted to high temperature type material systems. And then under supersonics and subsonic fixed wing, we're interested in making the fan case more multifunctional. Some of the basic features of these composites are such that we think we can incorporate performance capabilities like noise attenuation directly into the fan case, which would have additional system benefits by enabling engine manufacturers to remove other pieces of the engine that are in the engine right now for noise attenuation, for example. So those are the directions we're going now, and we think will ultimately lead to the next generation of composites in these types of applications. So with that, I'll bring it to a close, and I'd be happy to take any questions you might have. Thank you.
Hello, I'm J.D. Harrington, and I'll host today's question and answer portion of today's presentation. Before we get started, a short caveat, if you would, wait until we get the microphone to you, and then would you start by introducing yourself. With that, do we have any questions here at headquarters?
Dale, Murray Hirschbein, Fundamental Aeronautics. You were showing the big advances that you made in braiding and other techniques that were not available 20 years ago, but I also noticed you're using IM7 fibers and T700 fibers, which are pretty tough materials. What extent has the benefits of the composite fan case been enabled by the advanced fibers versus the advanced manufacturing techniques?
Well, the advances in raw materials have certainly, contributed to it. We haven't really tackled the problem at that level. We haven't tried to advance the raw material technology, but rather take the advances in raw material technology and use them in a unique way to really meet the requirements of the application. So
what extent has the fundamental advances of fibers over the last 20 years made this technology possible? If you'd done it 20 years ago with the fibers that were around then, this has been twice as heavy, I think.
it's hard to know. I mean, fiber performance has advanced. I don't know that is a would have been a primary factor in influencing the performance improvement. I think it's really more the new architectural forms that we've enabled using the braiding and fiber reinforced foam concepts. I think really contribute more to the performance improvements, as opposed to traditional approaches to manufacturing composites.
Any other questions? One over here.
My name is Jim Hookey. I'm with the National Transportation Safety Board. I was a power plants investigator. And as we get to investigate a lot of uncontained engine failures in the course of our work, and I'm wondering if there's a change in your testing that you have done. Have you seen a change in the dynamics of the blade in where it goes after it's released and it impacts the case on a composite structure versus the traditional structures that we see now?
And that's a good question. We haven't been able to get any insight into engine level tests with composite blades. Obviously, there's only one engine company that's flying with composite fan blades. That's General Electric. Their GE90 engine and their new GE NX engine will have composite fan blades as well. And they haven't shared much with us in terms of how composite blades behave versus titanium blades, which was the state of the art, prior to composite blades going into service. Now, obviously, the composite blade behaves differently as a projectile. In the physics of the impact of a composite blade on a metal case even are different than a titanium blade on a metal case. And certainly, a composite blade on a composite case is different than a composite blade on a metal case, too. So, where companies have shared engine test details with us, we've been able to fine-tune our testing methodology to try to match the real situation as closely as we can. But at this point, GE hasn't been willing to share the details of engine blade out tests for composite blades. So.
All right, another question here.
Well, also from Fundamental Era. You seem to highlight the certification process as being the major hurdle that the manufacturers have to overcome to use these types of systems. So to what extent are the advances in modeling and simulation impacting the time that it takes to certify these fan containment systems?
Yeah, I was rushed a bit at the end there. On my benefits chart, I tried to elucidate a little bit about that. Obviously, these improved modeling tools are allowing more accurate and faster design cycles. So the overall product development, design and development phase on a new engine, we think, and the engine companies are agreeing that it compresses that cycle somewhat. So you're saving cost and time, and as I mentioned earlier, we think we're taking risk out of the design and development process as well by providing these more credible simulation tools. So, and they have estimated savings, industry-wide. I actually had a figure on the chart. I didn't get a chance to really address it, but I think it was like $500 million annually industry-wide that they've estimated we have saved in the typical design development process. So.
Any other questions? I just happen to have one myself. The braided composites seem to have a real benefit for cost savings in that, but what about if they get damaged? Is there a repair capability to them, or do they have to be replaced?
Well, if they get damaged as a result of a blade out, it pretty much destroys the case. I mean, there's no attempt to try to salvage a case. The damage is too extensive. If it were to get damaged, if it were to experience more minor damage, like during the assembly process or something, the repair techniques for this would be similar to the repair techniques for other composite constructions, laminated constructions. So I don't think there is a distinct repair methodology issue for these versus more traditional composites.
Okay. One last check. Is there any other questions here at the headquarters? All right.
Steve Jacobson with Aviation Safety. In regards to the factor of safety that are required for composites versus metallic structures and airframes, do you have the same difference in the factor of safeties for these engine casings, or the advances in modeling, does that bring the factor of safety closer together for the two?
Well, our thinking is that it should allow that. It should allow the engine companies to reduce their conservatism. We've given them better tools I mean, these tools would be better for designing metallic cases as well. So we've given them better, more physics-based tools to simulate the event, during the design and development process. So we think even for metallic designs, it should enable them to reduce their safety factors. Now, clearly, they're not going to share their safety factors with us. Every company probably has a different safety factor, just based on their level of, confidence, if you will, with this problem. But we think we have enabled conservatism to be taken out. And the ramifications of failing the blade out certification test are just too huge to allow that to be a possibility. So there is a lot of conservatism in the design of that component for sure. By the point you get to a blade out test, you have already booked orders for the engine. It's committed to a particular airplane, so you can't afford to fail it. So there is a lot of conservatism built in, I think, into the design for that reason.
And looking at the clock, it looks like we're going to have to close out today's presentation. I'd like to thank Dale Hopkins for putting the presentation together and coming out from Glenn to give it to us. If you'd like more information about the NASA Aeronautics Program or projects, please visit us on the web at www.aeronautics.nasa.gov. Thank you.